where you are right there. Pause the video, earphones out. Give me a halfway close your computer so you can pay attention here. You know, willpower. I'll just look at the computer, sometimes that helps. So who feels like they kind of know what's going on with the law of conservation of mass? Law of conservation of matter. Okay, I'm gonna ask for a couple points that you guys gleaned from the video. We'll take maybe 5 minutes of notes just to elaborate on that process. We'll talk about question 5 on problem set 2 because it does relate to the law of conservation of matter. And I want to require that you like to know 100% how that was done without me reviewing first. Okay, so tell me something that was an interesting fact or a fact about the law of conservation of matter, Aaron.
Well, it means that mass can be created or destroyed.
So, sorry, I'm just really hoping my smart board works. Mass, okay. Mass cannot be created nor destroyed. Okay, so these are gonna be like your first part of your notes. So if you didn't write some of this information down, it might be just a key point that you would want to elaborate on for your own study purposes. So this is law of conservation of mass. Okay, mass cannot be created nor destroyed. What you got? Okay, so that's the one. I'm not even going to call it exception. It's the one elaboration of when we do have like a nuclear decay event. There is the nucleus of the atom is changing. The mass seems to be rearranged, but also it seems like maybe we lost it. Well, we actually didn't lose it. It has just transformed itself into energy, which is where we get E equals mc squared. This is not the most important piece of data, but it's one of the most interesting facts that we can now actually understand why E equals mc squared, right? E is energy, M is mass, and so there's this C constant right here. It's called the speed of light. We'll talk about that more next week, but the speed of light tries to account for the difference in mass and energy. What you got, Jacob? Tell me something interesting. Or a fact you learned. I mean, there's not a whole lot we're working with here. It's the law of conservation of matter. Does anybody have anything else they want to add to this? Yeah.
Loss of mass means release energy.
That's kind of what Isabel was just saying. Yeah.
On the video said that energy is equivalent to mass.
Okay, so the mass, the matter that's in existence can easily be transformed into energy by way of most of the time reactions. So let me go past the energy component of this for just a moment. Yeah, Evan.
Adding energy can rearrange the structure of maybe a molecule or a compound or something.
Okay, perfect. That word rearrange is what kind of I was looking for. Okay, so I'm gonna add on to this. Law of conservation of matter. Mass can neither be created nor destroyed. Comma, matter is simply just rearranged. And you guys saw that in a couple of the examples they gave you. They gave you some balanced chemical equations. One of them I'll actually do from maybe your homework. We'll do it like this. I'll do the decomposition of this. Gosh, what was homework? Number 5. Was it water makes hydrogen gas and oxygen gas, or was it hydrogen gas and oxygen gas make water?
Hydrogen and oxygen makes water.
Okay, cool. So hydrogen gas plus oxygen gas reacts, right? Chemically changes to form water. That's what this reaction is supposed to be giving us information about. We have these reactants, and we have this product. Your reactants react, and when they react, they rearrange their atomic structure, they rearrange their atoms and how they're bonded to each other, and they make a product. But we don't want to break the law, right? We're not lawbreakers, we're not criminals. We always want to make sure we have a balanced chemical equation, which would then allow us to see the fact that the H's over here, the H's in the hydrogen gas have just been rearranged to now bond with oxygen to form the H's in water. So Grant, how many hydrogens do I have on both sides? How many hydrogens on this side?
2.
How many hydrogens on this side?
2.
2. So far so good. Our two hydrogens have just been rearranged to form that of water. Kelsey, how many oxygens do I have over here? And how many oxygens do I have over here? 1, because there's a subscript of 1, and we normally don't write it. It's just assumed to be there. So we've broken the law, right? We have 2, and then we don't have 2 over here. there needs to be 100% transparency between the reactants and the products. They're the same thing. So what we can do now is we can add coefficients to the front of these chemical elements or compounds, and they're going to allow us to balance the equation. You've done this before, probably in like 7th grade. So since you see 2 here and you need 2 here, you cannot put a 2 subscript because that would make hydrogen peroxide, which is not the same as water. So we can't change the chemical formula. You can only add coefficients. So what do I want to add in front of water? A 2. And this 2 is going to then be distributed to the hydrogen and the oxygen because it's applying to everything past it. So yeah, we got 2 oxygens now, right? But now what do I have? 4. 2 times 2 is 4 hydrogens. So what do I need over here? Another 2, okay? So I have 2 times 2, so that's 4 hydrogens. 4 hydrogens, 2 oxygens. 2 is distributed out. Oxygens. What's the coefficient here? A 1. It's just assumed to be a 1. So we show the law of conservation of matter, or mass, sometimes it's called mass, sometimes it's called matter, but the law of conservation of matter by balancing an equation and considering the masses that we started with and the masses that we ended with. So in that number 5 on your problem set, it said you had 26.4, let's make this right, you had 26.4 grams of oxygen, and it produced 79.24 grams of water, okay? And it says how much hydrogen would have reacted, okay? So this is question 5. Solve this with me if you did not solve this on your own. This is one of your easiest math problems ever in chemistry. The mass of reactants equals the mass of products. Law of conservation of mass. It does not get destroyed or created. So this is an addition subtraction problem, okay? So the hydrogen gas plus the oxygen gas equals the products, which in this case is just water. So what do I do mathematically?
79 times 24 minus 26.
All right, so subtract 26.4 grams on each side. And that leaves us with, this was x, right? So x equals, what is it, 52.84? And so that's our grams of hydrogen. That's it. So law of conservation of matter, we're counting the atoms. Oops. Sorry about that. Law of conservation of matter, we're counting these atoms, H's and O's, H's and O's. Law of conservation of mass, we're still talking about the law of conservation of matter truly, but we're looking at the masses to see that the masses on the reactants are consistent with the masses of the products because they should be equivalent. Give me a double thumbs up if you understood everything I got up here. Okay, so in the sig fig portion of this is a subtraction problem. So do I regard sig figs or decimals? Decimals, 2 decimals, 2 decimals, 2 decimals, we're good. Okay, so that's why this is going to be recorded as is. Question. I just put X to represent the amount of hydrogen, like that's what we're solving for. And so I put grams hydrogen there to indicate the units of it. It's just we're solving for how much of the hydrogen actually reacted. Let me do another one like this, okay? So we have a reaction between, actually I have the reactions here. We'll just go forward here. I'm skipping that for a second. We did all that. We're going to do this one, okay? We're going to solve for the law of conservation of matter first by counting atoms, and then we're going to solve for the law of conservation of mass, which is essentially the same thing by solving for mass. So look at this equation, right? You recognize photosynthesis. So we've got carbon dioxide and water plus the sun yields glucose and oxygen. I've already given you the coefficients here and here. So I want you guys to tell me how many atoms of carbon, hydrogen, and oxygen are on each side of the yield symbol. So everybody, tell me how many carbons are over here. 6, because there's a coefficient of 1 behind it. So that's 6 times 1, so that's 6 carbon atoms. How many hydrogen atoms are there? So 6 times 2, because that 2 subscript is going to be included. So that's 12. How many oxygens? Count them again. 6 times 2. So that's 6 times 2, that's 12, right? And then 6 times 1, because there's a coefficient of 1 on this side. So there you go, 18. Does that look like a happy face? Okay. How many are on this side? How many carbons are on this side? 6, because they're nowhere else to be found. There's a coefficient of 1 in the front. So that's 6 carbon atoms. How many hydrogens? 12. There's only a 12 subscript there. And how many oxygens?
18.
You're hoping 18, right? Let's double check. So 6 times 2 is 12 plus 6, 18. So did we break the law? No. The matter has been conserved. It's just been rearranged. That's the word for that. Questions here? We will work on balancing equations much later. I just want to know that you see that you're able to do some of that. Okay, so this is a combustion reaction. So methane, cow farts. Okay, you saw that in one of the videos. Plus oxygen yields carbon dioxide and water. I've balanced it for you. So what I want to do for just give you some examples to work with is what if I said I had 2 grams of methane to start with and it combusted with 4 grams of oxygen. In that reaction, it produced 3.5 grams of water. 3.50 grams of water. How much carbon dioxide was produced? Think, work, no, don't ask for your answer, okay? So this 2 grams of methane reacted with 4 grams of oxygen. In that reaction, it produced 3.50 grams of water. How much carbon dioxide was produced? Go. You need a calculator. I have another there. 3.50. I'm trying to keep my safe distance. I really don't think you need a calculator, but
Yeah, is it not just
it would not be hard.
Wait, which one is the, oh, wait, we gotta do the next one.
Say again? All right, you have about 30 seconds to figure this out. 30 seconds. All right, Zoe, help me out here. How did you approach this?
I added 2 and 4.
Okay, so we took the reactants, we added them together. So the total of the reactants is what? 6.
I subtracted 3.
Okay, so the total of the reactants is 6. You said it equal to the masses of the total products,
Yeah.
right? But what did you plug in for this?
2.5.
Well, I know you can do the math now, but you just put x in for now, right? To make it something more like an equation. Okay, so then this over here being water, ignoring it, like, we're ignoring the coefficients. We're not using them at all. That's just for balancing. This is the mass, so 3.5. So you had your 3.5 for water, your x for your unknown, and your 6 for your total for mass of reactants. What did you do then? Subtracted 3.5 from both sides, and then what did you end up getting?
2.50.
Ooh, look at that. Decimals there. Okay. So 2.5 grams would have been the final by taking 6 minus 3.5. All right, so simple math, like 5th grade math. I don't know when you start subtracting, but it's really early. Okay, and moving on. That's really all I want to show you. We're not going to balance those right now. We're going to do our lab now, okay? Oh, no, sorry, lies. Problem set 2. Problem set 2. Let's check that real fast. Lies. Okay. If I call this out, it might be easier, or if I leave it up, it might be easier. So I'm gonna leave it up, actually. I don't know which is better for you guys to hear it or to see it. Start with 1. You guys see that?
Reading it's not so number C.
I'm gonna scroll down and let me get the record. gonna wait so people can see 3 and 4 for a moment. Can I scroll down a little bit, guys? Thank you. All right, so I'm gonna go down to Can I scroll all the way down to 2?
Yeah.
Okay, I can always scroll back up. Let me leave it right there for a second.
Or we need back up to 3.
I can go back up. So as you're going, how are you on 1? Alright, maybe just a quick, you read something wrong and then maybe you put mixture versus pure. Yeah.
For the color, can I have them both?
Yeah.
Which color was it? Which number?
B.
2B.
But physical, if it's
So color, you can put both because it needs to be a little bit more elaborate on what it's dealing with. You'd have to know the situation or the context of which color change occurred. Yeah. So I put physical property because it didn't tell me that it was like a precipitate forming this type of color. Okay. All right, I'm gonna scroll back up to 3 for a moment because I already did 5 for you guys. So you guys did really well on your Google Doc or Google Farm with the chemical and physical changes. So I don't think this is like your biggest trouble. I think financial analysis is still where you're most studying. Questions on 3? Yeah.
Maybe example of one color is for color change.
So a color, it has to. I have to like show it to you like in the lab. But that problem or the step 2 yesterday, is that where you guys had the sodium chloride, NaCl, in water?
Yeah.
Right. So you had sodium chloride in water. That just made a salt solution. And then, so you took your salt solution and you added to that silver nitrate. And actually, I can tell you what's happening here. So you actually took sodium chloride solution, aqueous, what that means, AgNO3, which is your silver nitrate. You reacted it to make sodium nitrate, which is clear. You didn't see that? But you also made silver chloride. It was a precipitate, PPT, and that precipitate was a white color. You added a clear solution of sodium chloride to another clear solution of silver nitrate. You made a clear solution, but in that clear solution you had a precipitate, which was white. You guys remember seeing the like snow? That was a white color, which is a color change, but that color change is not indicative of a physical change. It was indicative of a chemical change, because the color change here was a chemical change due to the fact that the precipitate that formed was white. It was a different color than expected. Okay, so that should help you a little bit on your lab as well. Those are sometimes hard. You can't predict them. You have to see them happen, and if you didn't expect it to change color, that should probably be a chemical change. Okay. Another one like that, since you guys have your lab out. 5. We all back to that step? Yeah? You had copper 2 sulfate pentahydrate, copper 2 sulfate pentahydrate, 7. You had this one right here. What color was that? It was step 5. It was blue, right? And you ground it up into the mortar and pestle, and then you heated it. So we put heat above the yield symbol to say that we're doing something to the individual reactants. And then what happened, guys? It turned white. And what else did you see happening? When you said liquefy, give me something more. What happened? Condensation. Okay, so there was liquid coming off the powder, right? It was evaporating off, but then it condensed on the side of the test tube. So what formed? What is that made of? What's the vapor made of? Yeah, water. Made of water. Okay. So we had this compound that was white, and then we had water that was forming on we saw it condense anyway, so we kind of knew it was water. So what was left over? Look at my reaction. Look at my elements involved. Water was pulled out. It was evaporated out. What's left? Cu SO4. So this was a blue color, and it transitioned to a white color. Would you indicate, seeing from here to here, would you say that's a chemical or physical change? Loud and proud? Chemical change. Yes, this was a chemical change because one, it changed color. So you're like, okay, it could be either. But when you think about what's happening, you had this guy that had water inside of the blue crystal, then you heated it up and you pulled the water out. What did you do to the crystalline's composition?
Change color.
Well, because you changed the crystal's composition, it changed color because it just is a different thing now. Like different things have different colors associated with them. So if you change the chemical composition, meaning like what the crystal in that case was made up of, you've changed its identity, and sometimes different identities have different colors. So the one with the hydrate with the water inside of it was blue, the one without it was white, therefore its chemical composition changed, and that color change would happen to be a chemical one, not a physical one. Who got that from the lab? Who got step 5? All of you. Say again? Well, you all got to step 5. How did you identify your chemical and physical changes? Evan, what did you guys get? What was your physical?
We grind it up.
Okay, so grinding it up with the Morin pretzel, changing the shape, changing the size is physical. What did you guys say is your chemical change?
Heating
Burning, I'm gonna say no, because if you burnt, did you burn your compound?
What?
What was burning that you're speaking of?
The crystals and
So you burned your crystals, that you weren't supposed to do that, right? So don't put that down.
the... No, we didn't burn them. I just...
But the temperature for the chemicals themselves.
So if we
Hold on a
just put
second.
color change and condensation,
Those are two different thoughts. Just one chemical. Yeah. But for the burning one, the heat applied should not be your chemical change because you're looking at this guy itself. I know you heated it up, but itself did not release heat or remove heat. And there was a little bit more there. The color change would be your best option for chemical change. The color change, it changed the composition, right? The compound changed from this to this. The carbon 2 sulfate right here. But if you include the fact that water was released, that helps justify how you knew that because you knew that it was been removed from the crystal itself. All right, so I'm going to wrap that for a second. I can take those labs at the end of class. We are going to do our law of conservation of matter lab. Okay, so pull up a piece of paper for that. You are practicing proving or disproving the law of conservation of matter with a couple of reactions. But quite fun. So I just have a couple of things to tell you before you go. The lab itself, in your lab notebook, says that you need a 600 milliliter beaker. Our scales just don't mass that high, so choose something smaller, like a 250 milliliter beaker could work. That should be fine, because most of those scales only go up to like 200 or 300 grams, so we just need a smaller beaker there. Everything in the lab is really well explained. There's 3 parts. You're working through 3 different systems. So the very first experiment, you have an open system, and then the last 2, you're going to have closed systems. And I think that was those 2 terms you might even use as you're explaining why you saw what you saw in the lab. You will be using a soda bottle, a 2-liter soda bottle. Rinse it out really well when you're done. Don't just leave your crap in there because my next class gets to use those. Put your trash in trash cans. You guys have been doing a great job cleaning the labs for me. All these chemicals, they'll be neutralized when they react. They are good to go down the drain because they're safe. They're not going to corrode the pipes. Whenever you're doing your percent error at the end, so I'm going to leave this on the board for you guys, but when you're using it at the end, I'm telling you what to compare here, okay? So use the mass of the reactants, and you're going to compare that to the mass of the products at the end, and you'll do your percent error from there. How do you do percent error? Actual minus experimental-ish, okay, over accepted or actual. Okay, I got most of that out of you. So we're going to modify this to look. We're going to modify this, which is the absolute value up there, sorry. We're going to use that down here. So we're going to do mass of reactants minus products, okay? What if the law of conservation of matter is followed, what should that be?
Equal.
They should be equal, so what should it be when I subtract? It should be 0. We'll see. We'll divide that by what? What should it be? What the reactants you started with, that mass, should still be in the products, right? Divided by the reactants, times 100, and get your percent, okay? So see how that reflects the same idea? Okay? So you guys will do that, and then we're gonna go to our lab. Okay, goggles, lab books. You guys are good. Same group for unit 1. But you have to check your data. You'll take your data and see how it works out. 'Cause it's probably not gonna be perfect. 'Cause, you know, it's our first law of conservation lab.
Do you have any tissues?
Yeah, I do. Over here, right there.
Alright guys, let me tell you which lab. There's 2 labs in there. 2, 1. And listen, so you're going plastic chemical distribution lab. I'm hoping it's the next sheet if somebody has a new lab. It looks like this, it's chew to a page and it has a bottle. You see like the 2-liter bottle and like a balloon on it. Make sure you're using the correct lab. I have so many labs.
There was one that said lost. There's one Who said to pull it off?
Oh, you just need, I just said you need it.
Oh, it's already.
So now are you getting
I'm checking for shoes now, so I can trust you. You guys need to get wearing shoes, like, what's going on? People bring shoes, but they forget to wear And I have my What did you say?